This is an introduction to log base 10. In order to get us started, I want to start with reviewing the powers of 10. You hopefully are familiar with these, but just reviewing what they are and how we can derive them. I'm going to start with the middle. I have this list of powers of 10. Obviously, this is not exclusive, but it is just some of the basic ones. Thinking about 10 to the first power, that's just 10. 10 squared, or 10 times 10, is 100. Cubed, 10 times 10 times 10 is 1,000. To the fourth power is 10,000. 10 to the fifth power is 100,000. If we were to go back down, working our way down, 10 to the 0 power, hopefully you remember that's 1. Anything to the 0 power is 1. Anything with a negative exponent is 1 over to the positive exponent. So 10 to the negative 1 is 1 over 10 to the positive 1, or just 1/10. 10 to the negative 2 is 1 over 10 squared, or 1 over 100. 10 to the negative 3 is 1 over 10 cubed, or 1 over 1,000. In decimal form, because this is often used, 1/10 is 0.1, 1/100th, 0.01, 1/1000th, 0.001. If you ever forget how to handle those negative exponents in the 0, one way to derive them is to think about going down the list and just dividing by 10. If we divide each of these by 10, if we divide 100,000 by 10, we get 10,000. If we divide 10,000 by 10, we get 1,000. If we divide 1,000 by 10, we get 100. 100 divided by 10 is 10. 10 divided by 10 is 1. And this is where it gets helpful. Remembering that 10 to the 0 power is 1 because 10 to the first power divided by 10 is 1. If we divide that 1 by 10, we get 1/10. If we divide 1/10 by 10, we get 100th. And if we divide 100th by 10, we get 1,000th. So that's where those come from. And one more thing I want to point out here is how the power itself relates to the number of decimal places. Starting here, the 5, we have 5 decimal places beyond the 1. So we have 5 zeros in that case. Here, 10 to the 4th power gives us 4 zeros, or 4 decimal places past 1. 10 to the 3rd power gives us 3 zeros, or 3 decimal places. 10 to the 2nd gives us 2. 10 to the 1st gives us 1. 10 to the 0 gives us none. 10 to the negative 1 gives us 1 decimal place to the left. 10 to the negative 2 gives us 2 decimal places to the left. And 10 to the negative 3, 3 decimal places to the left of 1, from 1. All right, so hopefully that'll help us as we do problems like this later. But next I want to just sort of define what logarithms are. A logarithm is a form of an exponential equation. We just use it as another form. The reason we might use it is, let's say we have something like 2 to the x equals, let's just say 10. In other words, what could we raise 2 to give us a value of 10? Now, if we had something like 8, 2 to the x equals 8, we might be able to figure that out by hand or by thinking, because we know that 2 times 2 is 4, and if we multiply that by 2, we get 8. So, in other words, 2 to the 3rd power, multiplying 2 by itself 3 times equals 8. So, in that case, x would equal 3. But if it's something like 2 to the x equals 10, we can't get an exact number just by thinking about it. If we try to divide by 2, if we want to isolate x using algebra, we don't really have a way. Dividing by 2 doesn't help. Subtracting 2 doesn't help. We need some kind of inverse operation of exponents. We need an inverse operation to undo these exponents. And solve for x. We need an inverse operation to undo this equation to help us solve for x. So the logarithm in base a of b is the power that a must be raised to in order to obtain b. So let's think about that in terms of this example. The power that a must be raised to obtain b. That's what we're looking for right here. We need the power that 2 must be raised to obtain, in order to obtain 10. That's what we need, and that's what a logarithm gives us. So that implies the logarithm in base a, or base 2, of b, or of 10, equals x. That's what this translates to. If we move more generally, if we have any base exponent, a to the x power equals b, we can rewrite that in log form as log base a of b equals x. Again, that reads log base a of b equals x. And what that did for us is it got the x out of the exponent. And we can use our calculator or some other tools that we have to find out, well, what is log base a of b? I want you to notice, and you should write this translation down. This is just two forms of the same thing, and pay attention, maybe draw some arrows connecting what goes where. The base of the exponent becomes the base of the log. The answer to the exponent becomes the argument. We call this the argument of the log. And the exponent itself becomes what the log is equal to. So you can take any exponential equation and rewrite it in log form by putting the base of the log as the base of the exponent as the base of the log, the answer to the exponent as the argument of the log, and the exponent itself as the answer to the log. That's generally for logs of any base or exponents of any base, but today we're going to focus specifically on base 10. So unless otherwise specified, logarithms are base 10, meaning the log of a number is the power of 10 that produces that number. So the log of b is the power of 10 that produces b. So in this case, I'm gonna just write that statement. The log of b is the power of 10 that produces b. We might have a specific example of that. The log, let's say the log of 1,000 is the power of 10 that produces 1,000. Well, what power of 10 produces 1,000? We can go back up here, 1,000, 10 to the third. So the log of 1,000 is 3. Another way to write that is the 10, that 10 to the x power, or to the third power, equals 1,000. Notice in these logs, there's nothing written as the base, as opposed to the example I showed you above where we had the base A. When there's no base written, it's understood to be 10. So no base means an understood base of 10. And so we could directly translate this, say this second example, the blue, where that 10 becomes the base of our exponent, because it was the base of the log. The argument of the log is the answer to the exponent. The answer to the log is the exponent itself. Logarithms and exponentials are inverse operations, so they can cancel each other. And that's really the main reason that logarithms exist, so that we can have a different form, a way to cancel out exponentials and solve solve for variables that are in the exponent. You can see here that since we have log with an understood base of 10 of a power of 10, the log base 10 and the power of 10 cancel each other out. That's one way to think of it. And the answer to this is just the exponent, just the x. Same thing here. We've got an exponent with a base of 10, and we've got a log with a base of 10. Those cancel each other out, and the answer is just the exponent. These are two other equations that you need to write down and have saved and memorize. That the log of 10 to the x equals x, and 10 to the log x also equals x. Those are just opposite forms of each other, and the log base 10 undoes the 10 to the power of x, giving us just the x. And the 10 to the log x, the 10 undoes the log, giving us just x. We're going to look at now some examples of applying these. So firstly, we're going to start with this example 1, find log 100 by hand and by calculator. So log 100 by hand, we're going to use the idea that if that last thing we just saw, that the log base 10 of 10 to the x equals x. So we want to rewrite, if we could rewrite this 100 as a power of 10, then that power would be our answer. So what power of 10 is this? We could rewrite log 100 as log 10 squared. Whoops, squared. And then, because of this identity rule, that the log base cancels out the base 10, and so our answer is just 2. Now on your calculator, if you're using a TI-84 graphing calculator, you have a log button along the left side. It is next to the left of the number 7. And in this case, you can just type in log, hit the log button, and then type in 100. Hit enter, and you see that your answer was 2. For number 2, we're going to find the log of 0.1 by hand. So we want to do the same thing here. We want to write that 0.1 as a power of 10. Log of 0.1 equals the log of 10 to what power? You can look back at your reference sheet or remember that's just 10 to the negative 1. So we're just starting by rewriting that argument as a power of 10. That's what we did over here. We rewrote the 100 as a power of 10, or 10 squared. Now we're rewriting the 0.1 as a power of 10, or 10 to the negative 1. And then, whoops, the log and the base 10 cancel each other out, and our answer is negative 1. And you can do this on the graphing calculator the same way. Hit the log button, type in negative 1, and you get, hit the log button, type in 0.1, and you get an answer of negative 1. All right, and then another thing that you will see commonly is you may be asked to rewrite things as base 10, or in the power as a power of 10. So if we wanted to rewrite 8 as a power of 10, we're looking for a way to do 8 equals 10 to some power. Well, again, if we look back at these identities, 10 to the log of something equals that something. So 10, if we could do 10 to the log of 8, that should equal 8, because the 10 and the log base 10 cancel each other out. So coming back here, if we had log 8 as our power of 10, then the 10 and the log would cancel each other out, and we just have 8. So we are asked to find out, well, what is that power of 10? So all you have to do is on your calculator hit log 8. It's going to give you a decimal value. And so we could write that as 8 equals 10 to the, you should have gotten 0.9031. We're asked for 4 decimal places, so 0.9031. And that's our answer. We've rewritten 8 as a power of 10. And you can check this. If you type in 10 to the 0.9031, now we rounded, so it's not going to be exact, but we're going to get close to 8. When you hit enter, you'll see that happens. And we do the same thing for part B. We just rewrite 800 as a power of 10 by writing 10 to the log 800. And then on your calculator, type in log 800 to find out what is the decimal value of that. And you get 2.9031. 2.9031. 800 equals 10 to the 2.9031. And you can also double check that. But your answer, all you're having to do is evaluate the log 800 or evaluate the log 8. Or in this case, evaluate log of 0.08. We're just using the log of 0.08 as our power of 10. And it's because the 10, the base of our exponent, and the log base 10 cancel each other out, giving us just 0.08. And so here you type in log 0.08, you get negative 1. So I'm going to write this as, I'll go back to my green, 10 to the negative 1.09. We need 3 decimal places, or 4 decimal places, which actually rounds us up to 70. Negative 1.0970 is another way to write 0.08. Okay, that's the end.